Right, we're doing module 1. So some functional group analysis and the acidity of organic compounds. Just a second. All right, so I'm going to start off with benzene. So that's aromatic chemistry. Then the acidity of organic compounds and some reactions of like alkanes, alkenes, and so forth. So let's see how much we can get done. And I want to work a few past paper with benzene. All right, so for benzene, let's start with this structure. So the benzene ring, like basically, it's cyclohexane, and they have alternate, double, and single bonds. Now, if you look in some books, right, well, you should see it in every textbook. All right, these two structures can be used to represent benzene. So if you notice, for this one, the double bond is here, here, and here. But in this one, it's in the other places, all right? The thing about the pi electrons, if you remember, double bond contains pi bonds, right? So the pi electrons, even though we give them a specific position in these two examples, they are not stationary. So the electrons are actually delocalized, all right? So these are possible structures. So when you have structures with two bonds, they are not actually stationary, all right? So what we draw is what we call a resonance hybrid. So to show that the electrons are actually delocalized, we just draw a circle inside of the ring. The circle is to show you that the electrons are not actually stationary. All right. So let's just get that out of the way. So this is the resonance hybrid. So we just say resonance hybrid. All right. So just know to draw these. So when you're going to do anything with benzene, you can draw any of these two structures. All right. It doesn't matter which one. All right. So now we get that out of the way. We're just going to name some compounds. All right. Just a second. So benzene is the parent name for any compound. If you have chlorine on it, so this is a chloro group. So we just say chloro benzene. By the way, functional group analysis and mechanism, it comes straight down to benzene. Right? So benzene is not excluded from it. If you check this syllabus under the heading functional group analysis, the reactions of benzene, it actually comes underneath it. All right, so this is chlorobenzene.
So,
Go ahead with the question. So this one, it would be bromobenzene. If you notice here, we don't have to put a number for this, for the chloro or the bromo. So when it's only one group on it, you don't need to the number. All right, so this now it would be 1,2-dibromobenzene. The naming of the compounds is not really a big deal for benzene, right? But some special compounds that you must be aware of now are these. So the benzene ring with an OH group, we call it phenol. Benzene ring with an NO2 group, that is nitrobenzene. Benzene with an amine group. For this one, it's called phenylamine. It has a common name, aniline. This one is methyl benzene. Common name is toluene. Let's second take off these compounds and then we move on. I'll give a minute. I can just take the picture of the board. All right, so I'm going to clear the board now and we continue. All right, so benzene, it has each position, it has a specific name that we give to it. Next class is on Friday. That's for module 2.
What time, sir?
I think I don't remember. I think 6. I will check and post it in the community section. But it's either 5 or 6.
Okay, thanks.
Right. All right. So let's say a phenol, right? Position 2. Position 2 on benzene. We call it ortho. Position 3, we call it meta. And position 4, we call it para. For example, module 3 will be Sunday, this Sunday before exam, before the Monday. So we have phenol here. If we have a chloro here, this is basically ortho chlorophenol. So it is 2-chlorophenol, but it is in the ortho position. So number 2 away from the phenol, that is the ortho position. Let us say we have methyl benzene, and we have something else. So we are adding our bromine to this position. All right, hold on. Let me not put it on this side. Let me put it on this side. So with the benzene ring, you can count clockwise, all right? And you can count anti-clockwise. So this position here, it is not 1, 2, 3, 4. It is 1, 2, 3. So these 2 positions on the ring, they are meta. All right. So when you're doing meta, ortho, and para, it is relative to the group that is already there. So these 2 positions are meta relative to the methyl group. So for instance, let's do it again. If the methyl group was here, then this is position 2. This is also position 2. So these would be ortho. Any of this or here would be the meta position. And directly in front of it would be the para position. All right, so just bear that in mind. These positions are relative where the group is. So if it is up here, then 4 is down here. But if it is here, 4 is across from it. So this is carbon 1, 2, 3, 4. So that would be para. All right, so we look at naming a few benzene. Now you know about the ortho, meta, and para position. This is important for you to know. So just remember position 2 from any group that is on the ring is ortho. Position 3 from the group is meta, and position 4 is para. So I'll give you a couple of seconds and then I'll clear the board. By the way, if you have any friends that say they can't get in, the class is now filled, so tell them they can view it on the channel. All right, so it's being streamed on the channel because the class is now filled. So let's continue again. Yes, it will stay on the channel. All right, so when a particular group is on the benzene ring, it can make the ring more reactive, it can make it less reactive. All right, so first we're going to look at the groups that we call activating groups. So these are substituents. Remember, anything attached to the ring is a substituent group. So the activating groups, these are substituent groups. I can just say substituents, all right, that make the ring
Sir, is that substituent groups?
oh yeah. Thank you for that. No, I am not talking at the moment. I am just writing on the board. All right, so the common examples of the alpha and para directors are the OH group and the NH2 groups. All right, so put those. So once you see them on the compound, they will be more reactive than benzene and direct incoming groups to the alpha and para position. So OH, NH2, and the methyl group. These are the only one you really need to know for keep, all right? Because these are the compounds that they use, all right? So anything which so phenol, amine, and methyl benzene, right? These are more reactive than benzene because they are activating groups. All right? So quick comparison, right? I'm going to put 3 compounds on the board. Before I do that, I have to give you activators. All right. If you haven't done, if you haven't finished writing on the left-hand side, just take a screenshot or a picture. I'm going to erase on that side. I won't be able to do all of module 1 tonight, but before exam, all of the broad topics that is for module 1. These are groups that makes the ring less reactive by pulling electrons from the ring. Now the deactivating groups, they are meta directors. And the main group you need to know about is the NO2 group. Because the NO2 group and the halogens. So the deactivating groups, they are meta directors. However, there's a point to note here, halogens, even though they are deactivators, the halogens are also para directors. All right, so halogen, it is a deactivator. However, unlike the others that are meta directors, they're actually also para directors. All right, so based on these two pieces of information, let me see if I can answer this question. If you were to arrange these three compounds in order of reactivity, from least reactive to most reactive, which one would be the least? Halogens are both orthopara. No, halogens are just orthopara vectors.
C then A then B, sir.
Repeat.
C then A then B, sir.
All right. Anybody else who want to share their answer? CAB. All right.
Also say CAB, sir.
Right. I agree. All right. Good. CAB. Yes, CAB is correct. So as we said, the chlorine is a deactivator, so it would make the ring less reactive than the regular benzene. So clearly, benzene is more reactive than chlorobenzene, while the methyl group is an activating group. So it will release electrons to the ring. So we just put a little arrow on it, pointing to the ring, to show that it releases electrons to the ring, whereas the chlorine is pulling electrons from it. So we just draw an arrow pointing towards chlorine. So a question similar to this was on a past paper. I don't remember which one. All right.
Could you please repeat that?
As in why it's C then A then B?
Yeah, sure.
Right. So remember, so CH3, what kind of group is it? Activating or deactivating? For the person that asked.
Activating.
Right. So that means once it is an activating group, it is going to make the benzene ring more reactive. So it has to be more, B is more reactive than A. The chlorine is a deactivating group. It is going to make the ring less reactive than benzene. So C is less reactive than A, and B is more reactive than A. It would be C, then A, then B, in the order of most reactive at the end. And out here, C, it is the least. All right, so if you get a question like this, just pay attention to which group is the activating group and which one is the deactivating group. All right, so by now you should know your activating groups, deactivating groups. Also, let me ask you one more before we move on. You're welcome. All right, so I'm going to put, let me see, two compounds. All right, let me do that quickly. All right, so take a screenshot now, and then I erase it. All right, so I'm going to erase it now. If I am adding Br to these compound A and B, I'm going to label the positions. You tell me your answer. So I'm going to label it A, B, C, A, B, C. So in compound A and B, if I want to add bromine to it, I want you to tell me where the bromine would go if it's A, B, or C in compound A and in compound B. Which of the positions?
Sir.
Yes, go ahead.
Sir, could you repeat the question?
Okay, all right, let me just put it underneath it. All right, when you send your answer, say compound for compound A. All right, let me call compound A number 1. All right, so this is number 1, this is number 2. Give me a second to plug in my laptop. B, 2, C. All right, so for number 1, if your answer is B, you are correct. So for number 1, it's B.
So, I want to ask a question. So the definition says it pulls or withdraws electrons from the ring. So is it that it's pulling the bromine from the meta position?
Wait, no, these groups, so when you want to add the bromine to the ring, if this group is already present on it, because so when we say it is a meta director, it means that when you're going to add bromine, the bromine will actually go here. All right. So when they do the experiment, they realize that when you have a deactivating group on it, 90% of the product produced is in the meta position, and like 3% and 5% in the alpha and para position. That's why they call it a meta director. So once you see NO2 is already on the ring and you are going to add something else, it will go in the meta position. So for A, once you see the NO2 group on it, you know it is a meta director, therefore the bromine should go at the meta position, which is 3 places away from your NO2 group. Is that clear?
Yes, it is. But what about the electrons that are being removed?
No man, that is what
Or-
makes, so in that it don't have the electrons. When we're doing this, the electrons being moved don't come into play. As in, that's not part of that part of the explanation is what makes it a deactivating group. So the move when you're answering it, you're trying to answer it, the movement of electrons towards this is not needed. The only way that would come about is if you're explaining your answer.
Oh, okay. Thank you.
Yeah. All right, so for B, if your answer is C, you are correct. So remember we said now the OH group is an activating group. So once it's already on the ring, if you're adding something else, it will, oh, sorry, for this one, if you put A or C, it's correct. Because remember, activating groups, it's not just para director, it is alpha and para. So A and C. All right. So that is where you would get most of them. All right. If you put ARC, it is correct because it is an alpha para vector. You will have almost equal amounts going in the alpha and para position. Not on the same compound, but on separate ones. All right. The OH, it's an activating group. That means you should know you have to put the bromine. All right. Hold on.
Here's a question.
Yeah.
Just for clarity,
Sure.
for meta and ortho para, directing means. It means that
Right.
when it's coming in, it's going to that position.
Repeat.
Okay, take for number 1.
Right.
That is meta directing, right?
That is correct.
Yes, so that just means that anything that's coming in is going to the meta position.
Right. Yeah. That's it. Yeah.
Okay. I'm just trying to understand for number 2 now because I was lost or I got my answer incorrect. For number 2, it just means that anything that's coming in is going to the ortho or para.
Right. Correct.
Okay, so
Yeah. So you can put it at the author, or if you want, you could put it at the para. Wait, that would not be para. So if the OH is here, para would be out here. Don't put, if you're putting A and C, don't put it on the same compound. So you draw one with auto, as I did here. So one auto and one para. Don't put auto and para on the same compound. All right. Yes, so for this question, all you need to know, right? Once it's a deactivating group and you're going to add something else, just put it 3 places from where the group already is. Who is that? So basically, need to know the examples of meta and alpha. Right. You have to know that it's meta or yeah. All right. So once you know this now, we can go ahead and do some reactions. All right. So the main part of benzene, the first part, the naming is not really a big deal because when you get the questions, they're more interested in the reactions and about activating and deactivating groups and so forth. So just know your activating groups and deactivating groups. And remember which is the meta position and the alpha and para. All right. And remember that once you have a deactivating group on it, it is going to make it less reactive than benzene. And if you have an activating group on it, it is going to make it more reactive than benzene. All right. So now that that is out of the way, we have 2 reactions of benzene, the nitration of benzene and halogenation of benzene. All right, so I will give you a chance to screenshot and then clear the board. All right, ready again. All right. Even though benzene has double bond, it does not react like your alkene. All right, so just know that we're short on time for explanations. All right, so benzene does not react like an alkene.
repeat that, sir?
I'm writing it on the board. Benzene does not react like an alkene.
Sir, we're still seeing the previous thing that was on the board.
You're not seeing reactions of benzene at the
No,
moment?
sir.
All right, let me clear and try again. Give me a sec. Let me stop share and then share again. Are you seeing it now?
Yes, sir.
All right, so current on the board, you're seeing reactions of benzene. Just check it.
Yes, sir.
All right, good. All right, so benzene, even though it has carbon to carbon double bond, it does not react like an alkene. Just bear that in mind. All right, that means it will not react with potassium permanganate. It will not react with bromine, just like that. So the two reactions for benzene that we need to know the halogenation, and in this syllabus, it asks for bromination specifically. All right, so if you have bromine, I'm doing the equation first, then the mechanism. If you have benzene and you want to react it with bromine, you are going to use a catalyst. The catalyst is FeBr3. And you will get a bromine attached to it. All right, so that's for the halogenation of benzene. The second one is the nitration of benzene. So if you want to nitrate benzene, you react it with nitric acid and sulfuric acid. An arrow. At a temperature of about 50 to 55 degrees Celsius, and you will get nitrobenzene.
Or 60 degrees Celsius, right?
All right, depending on which textbook, you will see anywhere from 50 to 60.
Okay.
Yeah. Anywhere from 50 to 60, depending on your source. Right, so this will be the equation, all right? So benzene with bromine, the catalyst, so FeBr3, that is your catalyst. So unlike an alkene, where you would just add it, you get a reaction for benzene that will not happen unless you have the catalyst. All right, so these mechanism, all right, so first the name of it. Name of the mechanism, electrophilic.
come here.
When you're doing the mechanism, you cannot use this circle. All right, you see with this reaction, there will be a precursor step, right? Where the bromine reacts with FeBr3, but that part is not a part of the mechanism. It starts when your Br2 is attached to the FeBr3, right? The first thing that happens is that your double bond here, and you can choose, right? But typically, use the one at the front. So if you put it here, this one will do it. You just draw your benzene, you have a FeBr3 that is bonded to your Br2 molecule. This one will develop a slightly positive charge, all right? So just put a positive charge on it. Once that is done, just like with alkenes, once you have the double bond, it will attack this, all right? It is basically removing the bromine from this complex, all right? Remember, whenever you're moving a pair of electron, you must use curved arrows. Remember, in reaction mechanism, you have curved arrows and you have fish hook. When you're moving a pair of electrons, it's the curved arrow. And you start from where the electrons are. So we're moving a pair of electron from the double bond to this bromine. So that is why you have the movement like that. All right. So at the end of this arrow, what you would have, now if you look, we used this pair of electron from the double bond. That means it is broken. And what you will have now is the bromine attached to the carbon. All right. These two bonds, they will stay in place. All right. So FeBr3 plus this bromine here, we just write FeBr4. It's a total of 4 bromine atoms that are bonded to it. So again, benzene removes the bromine from this complex. Once it does that, the double bond, it is broken because we use the pair of electron to get this bromine atom on the ring.
Sir, can you run through that again, please?
All right, so the bromine as the one of the double bond on your benzene ring, you are going to use it to remove the bromine atom. Once you do that, the double bond is broken. It no longer exists. So for example, if this is your double bond, right? It means you have 4 pair of electrons. You used 1 pair of them to take the bromine. So it is no longer in existence. All right. So you're only left with a single bond. So from here to here, you cannot have a double bond again. It was broken to form a bond with bromine. Understand? All right. So let's continue.
Yes, sir. Thanks.
All right. In step 2, let's put back everything as is. Double bond is here. Double bond is here. Br is here. And the hydrogen is here. Now, in some books, all right, so if you check like I am lost on the bond formation with bromine and hydrogen. Let me finish first and then I will do a simpler. I will jot the carbons and do it quickly and you will see it. Now, in some textbooks, so if you look at the study guide, when you read step 2, they will just show this, where you move the electrons. Give me a second. All right, so the electrons from the hydrogen will go back into the ring. All right. But the reason why that is happening is because one of the bromine from here is going to remove it. If you remember a catalyst, it is always regenerated at the end of a reaction. If FeBr3 is the catalyst, that means at the end of the reaction, we must get it back. So the bromine atom here, it is going to remove this hydrogen. And the bond between the carbon here and the hydrogen, it is broken with the electrons going back inside of the ring. So let's go up to step 1. The double bond was here. When it took up the bromine, it was broken. It looks like this structure. Now in step 2, what we are doing is reforming the double bond. To reform it, we need a pair of electrons inside. That pair of electron, it is coming from this bond here. Remember, in a curved arrow, it is showing the movement of 2 electrons. The 2 electrons in this bond is coming back here. All right. The bromine is removing this hydrogen. If you would do that, what you will end up with now is that the ring is going to be reformed again or completed back with the set of pi electrons. And the bromine is still on it. You get that plus HBr. Because remember, the bromine, it took off a hydrogen. All right. Plus, you get back your catalyst, which is FeBr3. So this mechanism, it's just 2 steps. Sorry, I was FeBr3. No, I'm not FeBr4. Just hold on, where's the marker? So right here we have FeBr4. This bromine comes off. So this bond is broken. The bond between this bromine and this Fe, it is broken. So this bromine combined with hydrogen. So let's do it again. This bond between this carbon and this hydrogen is broken. All right. So this hydrogen is no longer attached to the carbon. It is now with bromine. This bromine is no longer with Fe. You have the benzene, so you have bromobenzene, you have HBr, and you have FeBr3. So that is why we know longer of FeBr4. All right, what I'm going to do, I'm going to draw the structure of benzene with the carbons so you can see it. All right. I'm going to do it again, but I'm not going to, hold on. Let me just undo that and take a screenshot if you did not have it. All right, so just take a screenshot of the board. Yes, this is what you will draw. Right? But I'm going to do a different version where you can see the carbons clearly so you can understand what is happening. Okay. All right. So benzene, the formula for benzene is C6H6. All right. So carbon, 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 and the carbon is there. All right. So double bond, double bond, double bond. You have a hydrogen here, hydrogen here. Remember, every carbon atom must have 4 bonds. All right. So that is benzene without the skeletal formula. All right. So everything is clear now. All right. Let me erase the other side of the board. All right. So as we said, right, you have the Br. Have Br here. Good. With the positive charge on it. So that's the electrophile. You see this line here. Let me move it.
Sir, I think an age is missing. Someone said it in the chat.
Oh, thanks. Yeah. From up here, right?
Okay.
Yes, thank you. All right. So this black line here, I am using it to represent the pi electrons in your double bond. So this line here, it has 2 electrons, and I am using it to form a bond with this bromine. So this is a dative covalent bond where one atom donates 2 electrons to form the bond. So we are moving the 2 electrons from this bond to bromine. That means the double bond is broken. All right. The double bond is broken. You only have a single bond. And now we have the bromine attached to it. So we're forming a bond between the carbon and bromine. At the end of the process, bromine is attached. You still have the hydrogen there as well. Is it clear now as to what happened?
Yes, sir. Thanks.
All right, so let's just complete the ring. Put back the double bond here, double bond here. Single bond is going to be there. Which is here. Oh, I forgot to do something as well. This carbon here, right? How many bonds are around it?
3, sir.
3. So once it has 3, put a plus charge on it. All right. So in the second step now, what did we do? We have Br, right, attached to Fe, Br3. So a lone pair of electron now is going to remove this hydrogen. When it removes this hydrogen, the 2 electrons that were here, we're going to put it here. So you get back the double bond. Is that clear? Basically moving the electrons from here to here. That is how you get the double bond. And the positive charge will disappear. Is that clear?
Yes, sir. And then that forms HBr.
That is correct. So, what just happened? Right. So this bond is broken, this bond is broken as well. That is why you get HBr, FeBr3, and bromobenzene. No, sir. Destiny, you want to ask aloud so I can help quickly? All right, if you miss it here, let's do nitration of benzene because I'm going to do but the same thing again, 2 steps. All right, I'm going to do it again with nitration of benzene. All you're doing for when you're adding something to benzene, all you're doing using a double bond to take up an electrophile. Good. And in the second step, you take off a hydrogen. That's it. Two things only. You're going to take up an electrophile. When you take up the electrophile, the double bond is going to be broken, as I saw here. The second thing that needs to happen is that we need to put back the double bond. To do that, we break a carbon to hydrogen bond. That's the mechanism. You take up an electrophile by breaking a double bond. You reform the double bond by removing a hydrogen. So can I repeat? All right, so let me put a statement as to what happened. See if that can help. All right, so that is what basically happened. If you look at what step one says, one of the carbon to carbon double bond is used to form a bond with bromine. This converts carbon to carbon double bond to carbon single bond. Of a carbon to carbon double bond here, we used it to form a bond with bromine. When that happened, carbon to carbon double bond was converted to carbon single bond. All right. Then step two says to reform the carbon to carbon double bond, a hydrogen atom is removed from a carbon to hydrogen bond. And those electrons are used to reform the carbon to carbon double bond. So here you clearly see we are removing a hydrogen atom from the carbon to hydrogen bond. And the electrons in that bond are used to reform the double bond. So those are the two things that happened. All right, hope that is good for everyone. So just take a screenshot of the board if you haven't finished writing, and then we do nitration of benzene. Right, I'm going to start tracing now. All right, in nitration of benzene, basically these two steps will happen. The only thing we are changing is the electrophile. Honestly, to be on this safe side, know your mechanism, right? Even though they said functional group analysis, just do not have caution and do the mechanisms as well. All right. All right, so in this case, all we're doing is replacing the bromine ion with the nitronium ion. So this is the nitration of benzene. All right. All you're doing is switching the electrophile now. So the same thing is going to happen. One of the carbon to carbon double bond is used to form a bond with bromine. This converts carbon to carbon double bond to carbon single bond. All right, I'm going back to the skeletal structure now. All right, so you just need to remember that a hydrogen is here. And you put on the NO2 on it. All right, as usual, a positive charge is going to be here because you have just broken a double bond. All right. What is going to happen next? All right, all you need to do in step two, this, form back the double bond. All right. And so you get nitro benzene. All right. You mean the positive sign? No, you don't have to go inside of the ring. You just put it where the carbon is. You don't have to go inside. All right. So The mechanisms come, if it is looking difficult now, it's not. All you need to do, right? Draw your benzene ring, draw NO2 plus. You just draw a curved arrow to it, draw an arrow, put it on the ring. For step 2, you just draw a curved arrow from the hydrogen to where the double bond was. All right. Oh, by the way, don't do this. Don't use circles. All right. So we get back the double bond. All right. And for some books, it's hydrogen. They just put plus H plus. But if you want, it's actually sulfuric acid. All right. Could you list back the reagents and conditions? I'll do it shortly. All right. So look, if you're on the exam and the mechanism happen to come and you don't remember a lot, just draw your nitronium ion, you add it to the benzene ring, and just put back this. If you want, this is if you're going to write HSO4 minus and remove the proton. All right. But if you don't remember about HSO4 minus, all right, just make sure you're moving the electron and draw your nitrobenzene and put plus H plus. All right. And that is okay. All right. However, if you remember to put HSO4 minus and you remove a proton, don't put plus H plus, you're going to put H2SO4. So for this reaction, sulfuric acid is the catalyst. And at the end of a reaction, you always regenerate your catalyst. All right? No, you don't have to put it there if you don't remember it. All right? The key thing is just remember to put in your electrons back inside of the ring. All right? And you will get the NO2 plus. All right? And you write plus H plus. Good. So that's it. Just 2 steps. Accept the NO2 plus and then put the electrons into the ring. All right. And that's it. All right, so you can take a screenshot again. All right, so over here, right here would have been step 2. All right, so here is step 1. All right. I should know if you are wondering where the NO2 plus come from, just like with the halogenation, is a precursor reaction that is used to generate the nitronium ion. All right, so it is called the nitronium ion. All right, so that is your electrophile for the nitration of benzene. All right, so that is step 1, where you just take up the nitronium ion. And this is step 2, you take off the hydrogen. All right, so screenshot, and then I'm going to clear the board. Next thing we need to do now is look at the reactions of phenol. So no more mechanisms. These are the only 2 mechanisms that you need to know for benzene. All right, step 2 and step 1. I'm not sure what you're asking iPhone 8. All right, so remember, so the person that was asking, well, I'm going to work it in a past paper shortly. They're going to see it. All right, so let us move on to the reactions of phenol. All right, so 1 reaction of phenol with sodium hydroxide. Oh. So when you react phenol with sodium hydroxide, all you need to do is replace the hydrogen with sodium. All right, so that is it. So all you need to know is for phenol, we're just interested in you knowing the reagent and the product. So once you react phenol with sodium hydroxide, you are going to get sodium phenoxide. All right, that's how it is named. So the only thing that happens, you replace the hydrogen with sodium. All right, so that's one reaction of phenol that you should know. The second reaction of phenol is with aqueous bromine. All right, same thing as bromine, bromine water. For the first one, the sodium ion of sodium hydroxide is displacing the hydrogen. That is why you have this sodium here.
Sure. So you have to show the minus and the plus.
Yes, it is charged. But I don't think you should lose any marks if you just put ONA.
Yes.
Yeah. Right. So for these, no more mechanism. The only two mechanism in this section is nitration and halogenation. For these, just ensure you remember the reagents and the products that will be produced. This part, right. For this one, we're going to get 2, 4. All right. What would be the name? Let me see if I can tell me. What would be the name? What would be the name of it?
Sir, 246 tribromophenol.
Right. Two, 4, 6 tri bromo. All right, with this for observation, one, bromine water is decolorized. 2, white precipitate is formed. And 3, it will smell of antiseptic, or you say antiseptic smell. All right, those are the three observations that you should know.
Sir, could you repeat number 2? The
Number
reaction,
two,
sir? The reaction for number 2.
in terms, sorry, someone was mentioning this, they're correct. You use 3 moles of bromine. For the observations, the bromines, this bromine here, it is going to be decolorized. The 2,4,6 tribromophenol, that is the white precipitate. All right, it has an antiseptic smell.
So I was just wondering where the 3 bro, that's right. And the 3.
Right, yeah, so that is, I put the 3 in front of it. You should get this as well. All right, but the major part of the reaction is this, or the major product is a tribromophenol. And for this, it is this sodium phenoxide. All right. So there are 3 reactions of phenol, well, 4 that you must know. These are the first 2. All right, so if you haven't finished writing, just take a screenshot for me. All right, I'm going to clear the board now. Yes, the 3HBr is a part of it. That is only module 1. All right, so the third reaction of phenol is with acid chloride. And the example we're going to use, it is called ethanol. So this is just an esterification reaction, except that it's not a carboxylic acid. So remember, in a carboxylic acid, you would have the OH here. So what is going to happen? The Cl and the H are going to combine, right? So we are taking off the H off of the phenol. So you're left with O. Then we are taking off the chlorine, all right? So the carbon here is going to be attached to this oxygen. All right, so that is it. And this is phenyl ethanoate. So acyl chloride is just like an esterification reaction. You are taking off the chlorine, you are taking off the hydrogen from the phenol. You just put the oxygen where the chlorine was. So remember the chlorine was here, that is where you put the oxygen. All right, and that is it. So that's phenol with acyl chloride. So that's the general name of this type of compound, acyl chloride. It's basically a carboxylic acid in which the OH is replaced with chlorine. So let me just write that. Here, acyl chloride. All right, this compound is formed simply, you take off the chlorine off of ethanol chloride. All right, so take off chlorine, you take off the hydrogen off of phenol. You put the oxygen of phenol where the hydrogen was. All right, that's how we got this compound.
Sir,
Yes, go ahead.
so the other product is HPL?
Right.
Okay.
Right, so those are the three for phenol. For now, there is one more I'm going to show you. All right, so take a picture. I'm going to clear the board. You should also know this reaction as well. Reduction of nitrobenzene. For this reaction, we use tin, and HCl. And you will get amine. All right. So to go from nitrobenzene to phenylamine, you will use tin and HCl. Ensure you know all of your reagents for these reactions. All right. So we're going from nitrobenzene to phenylamine. All right. All right, so for phenylamine now, we have a particular reaction that I want to look at. Well, we have to look at. So this is a reaction of phenylamine that you must know. For this reaction, you are going to react the phenylamine with nitrous acid. So HNO2 is nitrous acid. So we are using nitrous acid and not nitric acid. So it's nitric acid, sorry, nitrous acid and hydrochloric acid. For this one, the temperature must be really cold. All right. In the study guide, it says below 10. Other sources say below 5. All right. So it must be cold. And what you are going to get you're going to have a nitrogen compound. Well, the nitrogen atom, you're going to have a triple bond, nitrogen and Cl. So just remember this structure. All right, so for some reactions, they just have reagents and not a particular condition like temperature or catalyst. So for this one, you must remember the temperature and the reagents. So for the nitration of benzene, you must remember the temperature as well. For nitration of benzene and for this diazotization reaction, you must remember the temperature as well. Not -5. It must just be below.
So you meant halogenation or not nitrogen?
Sorry, must be below 5 degrees Celsius. All right.
Sir, you said we should remember the temperature for nitration reaction.
Remember, nitration was 50 to 60.
Oh, okay. So
Yeah.
1 hour.
Yeah, man. On this compound here, with the nitrogen triple bonded to nitrogen, is called the diazonium salt. All right. It is called diazonium salt. All right. So the name of the reaction is diazotization. So phenylamine with nitrous acid and hydrochloric acid, we are making a diazonium salt. For these reactions, just study the reagent and the product. All right. It is the main product. You will get water as well, but that's not important. All right. So it's basically the main product we focus on. Right. That is where I'm going now. All right. So for phenylamine, we are going to form a diazonium salt. Now, if you remember, I said that we have a fourth fraction of phenol. This book says below 10, the study guide. It says way below 10. All right, so if you put below 10, below 5, that's okay. Because the temperature, it must be low. So when you use different sources, it will vary slightly, not by much. Yeah. All right, so the final reaction now that we are doing is coupling. And it is going to be a reaction between our diazonium salt and phenol. When we're doing this one, we draw it sideways generally. All right. So in this one now, we're basically going to join up the phenol with the diazonium salt. So all you need to know to do is draw the structure and remember your reagents. So after coupling, you will have nitrogen, double bond, nitrogen. You see this salt here, we're going to attach it to carbon number 4 of your phenol. All right, it goes to carbon number 4. All right. This compound here, where you join up phenol with the diazonium salt, it's an azo compound, or we say an azodie. It's an azo compound, or we just say azodie, because it is actually a dye. All right, so it is a brightly colored compound. Color is orange. All right, so all right. It's an orange color. All right, so let's just look back at the reactions that we did. And because we're going to work some past paper with benzene. So we should know the nitration of benzene, in which we used sulfuric acid, nitric acid, 50 to 60 degrees Celsius. We looked at the halogenation of benzene, in which we use FeBr3 as the catalyst. We looked at what else? For phenol now, we looked at the reaction of phenol with sodium hydroxide. You get sodium phenoxide. We look at the reaction of phenol with acid chloride, specifically ethanol chloride, and you get your ester, phenyl ethanoate. We look at the reaction of phenol with bromine. You get the 2,4,6-tribromophenol. We said that compound, it's a white precipitate, has an antiseptic smell, and it decolorizes bromine. And then for nitrobenzene, we can reduce it to phenylamine using tin and HCl. For the phenylamine, it can form a diazonium salt if we react it with nitric acid and HCl at low temperature. All right. And then finally, we have our coupling reaction between the diazonium salt and phenol. which we get our azodide. All right, so now we are going to work a past paper question. All right, so we're going to start with one from 2019. Yes, take a screenshot if you want. I'm going to clear the board. And these questions, they tend to come in our reaction scheme. You're going to see what I mean. I can clear everything.
So which question we're at 2019?
Yeah, 2019 number, I don't know, it's number 1, part C.
Okay, sir.
Yeah.
Which question are we doing or will be doing again?
2019. All right, so the first thing it says, so we have our reaction scheme from nitrobenzene going all the way around to compound E. The first thing we need to do is identify reagents. All right, so reagents for, so we need reagents for I, and I. All right, so going from nitrobenzene to phenylamine, what are the reagents for that?
Tin and hydrochloric acid.
Right, tin and HCl. And then going from phenylamine, all right, what compound is this? I'm going to put a C over it. What is compound C? Anybody know?
It's a diazonium.
Right, that is correct. They just switch up the formula on you. So the N2 that you are seeing here, it's N dash 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 N, Cl negative, positive. So they just chose to write N2Cl, but this is actually it. All right, so you're correct. All right, so if you know it is a diazonium salt, right? What do we use to go from the phenylamine to the diazonium salt?
Nitrous acid and HCl.
All right, HNO2 and HCl. And for part 3 now, which compound is this? What class of compound is compound E?
Coupling reactions.
All right,
Isodie.
right. So how do we get an azodie? Right, so remember we have our
We add the
diazonium salt.
diazonium salt.
Right. So we have it already here. So what would you react the diazonium salt with to get this compound?
Phenol.
Right.
Phenol, sir.
That is correct. All right. The next part of the question now, let me see if I find it. Where was it? Give me a second. Where was that it? Give me a second. Oh, so it also asks for a commercial use of compound E. So it would be used for dyes, as you know. Right. All right, so that was it for benzene. Have a question?
Yes, sir. Sir, the class of the compound is as a compound or
Oh, yes, as a compound.
okay.
Yeah, if I want to put as a dye. I'm going to switch to 2060 now. All right, so just take a picture of the board. Right, so right here, you can put used as dye in the clothing industry. So if you want to specify the industry, that's fine. Right, so I'm going to hit the board now. Right, and we're moving now to 2016. And this was number 4. So 2016, number 4. So it's a reaction scheme again. So when these questions come, we tend to have a reaction scheme. So you can see you don't have anything to worry about for benzene. Just study the two mechanism and know your reagents. Oh, in the question we did earlier, we put phenol. It's under alkaline conditions. You can put sodium hydroxide. All right, so here we go. Take the type of reaction labeled 1 and 4. All right. So for the exam paper, it said 1 and 4, but I'm going to include 3 as well. All right. So I wanted to tell me 3 as well. All right, so reaction labeled 1. What is it? So over here, reaction labeled 1, going from methyl benzene to bromo, methyl benzene. What is it? Right, halogenation. Right. So this reaction here is halogenation. All right, how about part 2? This reaction here, what is it? And from benzene to nitrobenzene. Anybody?
Nitration of benzene.
Right. And number 3, from nitrobenzene to phenylamine.
Reduction of nitrobenzene.
Right. And number 4, what do you think is forming number 4? Which compound?
The azo dye.
No, the dye is over here.
The diazonium salt.
That is correct. And what is the name of that reaction?
Diarization.
Right. Right, so those are the reactions taking place. The next part of the question now, list the reagents and conditions for reactions 2 and 4. I can put that here. Right, so step 2, right? So for nitration of benzene, right? What are the reagents?
Conc nitric acid and conc HCl.
Right. What is the condition?
Sir, 50 degrees, sir.
55 to 60.
Right. Concentrated sulfuric acid. Right, I'm going to put the range from 50 to 60 degrees Celsius. So that's for 2. For 4, what is the reagent?
Phenol.
Oh, not here, going from the phenylamine to the salt. Remember, this is the diazonium salt. So what do we react the amine with to get the diazonium salt?
Oh, the tin, sir.
Nitrous acid and HCl.
All right. And the temperature?
Below 5 degrees.
HCl. The study guide said -10, so let us work with the study guide. Since it's connected with CXC. So below 10. Right, so the study guide says below 10. So let's work with. Below this say much below 10. Below 10, below 5. You can pick one on the exam if it comes. Right, so those are the reactions and conditions for 2 and 4. Right, what would have been the reagent for number 1? For number 1, from methyl benzene to 4 bromo methyl benzene, it would have been what? Bromine and FeBr3. This was not a part of the question, but it could have been. Right, FeBr3. And then it asks us to draw the displayed formula of compound X. The compound X, right, all I need to do, take off the 2 hydrogen, triple bond it to a nitrogen, add a chlorine, minus over that, plus over that. So this is compound X. And then it asks us to do nitration of benzene in the last part. All right, so this is the typical reaction, but I'm going to do one more. Look, 2018, we have a table. So let's just do that quickly. All right, just take a picture of the board. Right, so in 2018, we have a table. By the way, the syllabus says PR2 and FE PR3. But you can also, if they should ask, it's not in the syllabus, but if you get chlorine, you can also use AlCl3 as the catalyst. All right. The syllabus did not mention it. I'm just including it. So chlorine and AlCl3 or FeCl3. So if they give a chlorine instead of bromine, you can use FeCl3 or Fe or AlCl3 to get chlorine. So let's go to 2018. All right, so for this one, it's the reaction of phenol, right? So they gave us phenol. Right. So we have phenol, right? So when you react phenol with bromine, that would be the three observations for phenol with bromine.
A pungent scent, smell.
Precipitate.
Right? So they describe it as antiseptic.
It decolorizes the compound that is in the
Yeah,
phenol.
give me a second to mute that person. Mic is on. All right, so antiseptic smell, you said, yeah, white. Somebody mute the mic, somebody's mic is playing the, right? Decolorizes bromine. Um, all right, that person, it might, where am I in myself? Give me a second. Give me a second. All right, let's go again. All right, so as I said, the bromine water will be decolorized. Right? In terms of structure, that would be the structure when bromine reacts with phenol.
2,4,6 tribromophenol.
Wonderful. All right. And when it reacts with sodium hydroxide, of course, it would be
O minus Na plus.
right. All right, so that's it. All right, let's try some other questions from other functional groups now.
So just draw those, right? Those structures in the box.
Right, that is correct, because those are the product. So you don't need to put any water or HBr. These are the main products. All right, I'm going to share the screen now. All right, so this product here is for sodium hydroxide, and this one is for bromine.
Sir, so what are the observations for sodium hydroxide?
They did not answer any, as you wouldn't get it. It's basically an acid-base reaction. So if you don't add something to it, like an indicator, right, you wouldn't see a change.
Yes, sir. Thanks.
That is why they put it out on the paper. Right, so that is where I'm going to leave it now for aromatic chemistry. So this
sir,
is, yeah, go ahead.
so sir, for the observation, we can just write out something saying no, some days see.
No man, they cross it out, you were not required to put anything. On the exam paper, it was blocked out. So you were only required to put observation for bromine and none for sodium hydroxide.
Okay, sir.
Yeah.
Sir,
Yes, go ahead.
sir, do you know that sir was saying if you saw like some of these organic questions on unit 1 paper based on how the syllabus was a few years ago?
Yes, back in the early 2000s, some of unit 1 was unit 2, vice versa.
Sir, and you think it's good if we could if we go back to them, right? Because
No problem, man. Once it's organic chem, it doesn't matter which year. Yes, so it still applies. It's just that they change up this syllabus and put certain things from what was unit 1 then in unit 2. But yeah,
Yes,
once it falls in unit 2 now, it doesn't matter which year it is from. Okay. So yes, so
okay,
you can practice them. All right, let us see how much you remember now apart from benzene and phenol. Remember, you have alkane, you have alkene, alcohol, right? Carbonyl compounds. You have the haloalkanes. All right, and next night I'm going to do esters and carboxylic acid. We have polymers to do and the acidity. Right, I probably have to do one Thursday. I'm not sure yet, but just look out for an announcement on the channel or your friends. All right. So alkanes, quickly, the reactions for alkanes now. Right. Let me do this. I'm going to put a compound on the board. I'm going to start with the alkene. So you can react alkenes with bromine water. You can react alkenes with liquid bromine. You can react it with water. You can react it with cold, acidified. We can oxidize it. We can add HBr as well. And we can add H2. And so there are 7 things that we can add to our alkene. Right? So all of these are for alkenes. Now what you should do, right? Which compounds are present that can react with a next functional group? So do we have any reagent here that reacts with something other than alkene? All right, so this can react with alkane. Alkane. This, and you can have hydrolysis of haloalkane. And these two, it can react with alcohol. You have to bear in mind the reagents that are common to other compounds. All right, so what we're going to do now, all right, let me take off one of these carbons, or not. All right, so Br2 aqueous, right? What would be the structure? All right, so CH3, C, CH3, all right, and then C, CH3. Let's put the H down, all right, doesn't matter. A question, when I react bromine, right? Let me label the carbons. A, B, for Br2 aqueous, which of the carbons, all right, what will I get? So every time I react an alkene with one of these, I must be adding 2 things to the alkene. So when it is aqueous bromine, what am I adding to the carbons of the double bond?
Br and OH.
Br and OH is correct.
Bromine.
Right. All right. So this is your alkene. If you're asked to draw the structure of the compound when a particular alkene reacts with specific reagent, all you're doing is breaking the double bond and adding 2 things to it. Because it is aqueous, we are getting the OH from the water. All right. So when it's aqueous, it's Br and OH. So this is the structure for number 1. All right. You can just take a picture. I'm going to erase it and do number 2. All right. So for number 2 now, what should I change about this structure?
Let's put on BR in the place of OH.
When you
All
OH,
right.
it's taking a BR.
That is correct. So when it's liquid bromine, it's it's 2Br that we're going to add. Right? Moving on to number 3. When it is water, what am I adding? Which two things?
H plus OH.
Right. So I am adding H and OH. So even though it's water, H goes to one carbon and OH to the next. Right? So that was for number 3. How about number 4 now? What am I going to add?
You're removing the hydrogen and adding another OH. So both
That is correct.
OH.
So when you use cold potassium permanganate, you get a diol. All right, so that's number 4. Soon do number 5. How about number 6? All right, let me check the comment. All right, number 1. Sorry, number 1. Because somebody was asking. So for number 1, when it's bromine water, you will get Br and OH. When it's bromine water, it's Br and OH. All right. Yeah, continue now, the person that was talking. So for HBr, what should I do? So number 6,
So would
what
you
should
would you add a hydrogen to one of the carbons and then bromine to the other?
which carbon is the bromine? BRC.
If there's a specific carbon.
Yeah. All right. So let me just remind you of Markovnikov's rule. Let me see if it can hold. When adding, I'm just going to put HBr, but he actually says when adding hydrogen halide. All right, let me just write it here. Right, when adding hydrogen halide, one alkene, so when you're adding hydrogen halide, in this case, HBr, you're going to put the hydrogen on the carbon of the double bond with more hydrogen. So looking at this, carbon, right? So over here, looking at these two carbons, right? Which one of them have more hydrogen directly attached to it? A or B?
B.
Right, because B has one hydrogen attached to it, C has carbon, the next carbon attached to it. I mean A. So A does not have any hydrogen attached to it. B has one hydrogen. So we always put the hydrogen of the hydrogen halide on the carbon of the double bond with more hydrogen. So this has 1 and this has none. So this has 0, this has 1. So you put the hydrogen on this one, the bromine on this one. All right. So as long as the carbons of the double bond have different amount of hydrogens, put the hydrogen on the carbon that already has more hydrogen. All right, so take a picture again, and then we do number 5. Oh, there was a 7 as well, H2. So this was actually 6. So this was not 4, this was for number 6. And 7 was H2. Okay, so let's do 7 now.
So you add a hydrogen to each of carbons.
That is correct. So for these, all you need to remember is all the reagents and the products that will form as a result. All right. I'm going to clear the board now and do number 5. So what number is that? It's there now. Hold on. Let me see about the structure of the alkene. When you use hot, does anybody know what happened when you use hot potassium permanganate?
So you're gonna get a ketone?
You don't must get a ketone.
You could also get a carboxylic acid.
Right. All right. So the first thing I want you to do, right? If you get the alkene and you are going to react it with hot potassium permanganate. Right, just a second. So this one is for hot AMNO4, which is oxidation. I want you to break the double bond. All right. They are cutting the molecule in two at the double bond. And then for the carbon of the double bond, this and this, right? Just wanted to write C double bond O. So convert the 2 carbons of the double bond to C double bond O. And then you're going to put back what was already on it. For this carbon, right? So that's it. So these are the 2 carbons of the double bond. Then put back what was there. So a CH3 was there. The CH3 was also here. This is a ketone. Once you get a ketone, that is the final product. All right. Now this one, it has a hydrogen attached to it. All right. And it has a CH3 group. Which compound is this?
An aldehyde?
That is correct. And what do we know about aldehydes? They are easily what? Aldehydes are easily oxidized. So this is not your final product. So for the ketone, let me just make a note. When you get a ketone, that is the final product. When you get the aldehyde, not final. All right. What is going to happen? It is going to be further oxidized to a carboxylic acid. All you're going to do is put an O where the H is. So the only thing you're doing, the only difference between the aldehyde and the carboxylic acid is that instead of an H, we'll have OH. That's it. Now this is final. Right? And that is final. So for the oxidation, of alkene, hot potassium permanganate, if you get a ketone, that's the final product. If you get an aldehyde, it will be oxidized to a carboxylic acid. That is your final product. All right. But there is one more thing I need to show you that is an exception as well. You can get ketone, you can get aldehyde. However, right, so I need to point out something else. Yes, that is what I'm going to explain now. To say that this is our alkene. So again, cut the alkene in two. So you will get, we have this CH3 here. As usual, the carbon of the double bond, you put double bond O on it and attach what is there. This is an aldehyde, again, you convert it to a carboxylic acid. This here, again, you will get C, double bond O, H, H. This is methanol, it would go to ethanoic acid. Now, this is the only one, this is the only acid that is going to break down to give you CO2 and water. So this is ethanoic acid. Once you get it, do not stop there. We'll go further to carbon dioxide and water. Right? Now on the exam, you do not need to go through all of this. They will just ask you for the final product, the CO2 and water. This is what you will do.
That's if you have to do some chemistry, some of us school come have exam on them.
Once you spot two hydrogens, once you spot two hydrogens, the carbon of the double bond, I'll take a screenshot and I'm going to tell you what to do. Right, so just take a screenshot of the board. All right, I can clear now. So if two hydrogens are attached to the carbon or to a carbon atom, the carbon to carbon double bond, all right, so once you spot two hydrogens attached, just like you see here, this should give you CO2 and water.
Sir,
Yes,
when I finish, I can go back to the slide before, please. I got kicked off. I want to say,
actually erase everything.
oh, okay.
Okay.
Thanks.
You can send me, after class, you send me an email and you a screenshot.
All right, so thanks.
Yes.
It's on YouTube, right?
It will be, yeah, it will be, oh, okay, cool. In this compound, all right? So the next rule, if one hydrogen is attached, one hydrogen is attached, we will first get aldehyde, then carboxylic acid. So paying attention to this carbon now, with no hydrogens, no hydrogen is attached, you will get ketone. Right, so one hydrogen, get your carboxylic acid. No hydrogen, you get a ketone. Two hydrogen, you get carbon dioxide and water. And this is oxidation with hot KMNO4. Right? Take a screenshot for me. All right, let me so we can quickly explain acidity of organic compounds to you, and then we wrap. Everybody have it already, right? Check in. Okay.
I wasn't finished. But I have the three so if you want to move on.
Yeah, all right, then good. And for this, we're going to compare alcohol, phenol, and carboxylic acid. Before I start the explanation, just going to make this point. Right, so alcohols, phenols, and carboxylic acid. Explanation, this is what we are going to use to determine which acid is stronger. The delocalization of the negative charge. Delocalized mean how it is spread out, right? So let's start with the alcohol. All right, so we know that acids are proton donor, right? So that means it's going to give up a hydrogen ion. So what makes the acid weak or strong? When we use the term strong here, just to point it out, carboxylic acids, all of these are very weak acids. So when we talk about strong, it's basically the strongest of the weakest because all of them are weak. But when you compare the three of them, carboxylic acid is the strongest, alcohol is the weakest. Remember now, we said that the more localized the negative charge, the stronger the acid. In alcohol, this negative charge is not delocalized. It's completely on the oxygen, right? Therefore, it can easily take up back the hydrogen ion. Because it is centered around the oxygen atom, it can easily take up the hydrogen. For a solution to be acidic, hydrogen ions must be present. So if the hydrogen ions are going to be taken up back easily to form back the molecule, then the solution cannot be acidic. So on the exam, I get 3 compounds. You need to explain why one is stronger. All right? To get an alcohol, this is what you will say. Let me get some space on the board. So this is why alcohol is going to be the weakest one. Just a second. So the negative charge This is just for the alcohol. All right. So this is the reason why alcohol is the weakest. All right, so that's it for alcohol. Take a screenshot if you're not finished writing. If you're on the exam, you forget something, you can put no. So this is a really short answer. If you forget your explanation, just put no delocalization of electrons. If you forget what to put for an explanation, just put no delocalization of electrons, all right, or of the negative charge. So if you cannot remember all of these pointers, all you need to remember, this negative charge here is on the oxygen. That is why it is weak, it can take up the hydrogen. You don't have to remember this point for point, right? All you need to say, the negative charge is completely on the oxygen, so it takes up the proton easily, all right? You don't have to remember all of these pointers. Just remember that the negative charge is completely on the hydrogen, completely on the oxygen, so it can take up the hydrogen easily. All right, so that works as well.
Sir, this will be uploaded to the channel, right?
Yes, it is already streaming on it, so once we end, it will be there still.
Okay, sir.
So the negative, so this is keeping it very short. The negative charge is on the oxygen atom, is on the oxygen atom only. So it can take up the hydrogen ion easily. All right, so just remember this for the exam. The negative charge is on the oxygen atom only, so it can take up the proton easily. All right, just remember that. You're welcome. All right, just take a screenshot for me again of this if you haven't written it. I'm going to play the screen. All right, so I'm going to play the screen now. So for phenol, all right, let me do the carboxylic acid. Just bear in mind, right? The alcohol, the negative charge was on the oxygen only. It takes it up easily. In your carboxylic acid, you have two oxygen atoms. The negative charge is going to be distributed between the two of them. All right, I'm going to put a broken line here. Remember, in the alcohol, the negative charge was only on oxygen. So in the exam, you can't remember stuff. Just remember the carboxylic acid, the negative charge is distributed between the two oxygen atoms. All right. So it cannot take it up as easily as in the alcohol. Remember I said, once it is delocalized, mean is distributed, it is a stronger acid. And the reason is that if you distribute it, you cannot take it up as easily. All right. So for the acid, let us write. All right. Come on, I'm going to write it now. All right, so just remember that the negative charge is distributed between the two oxygen atoms. All right, once it is distributed, it does not take it up easily. So this is what makes the acid stronger. All right, so let's do phenol now.
Sir, sir, the first one that you wrote, sir, is it a ketone?
Carboxylic acid, but it gave up the hydrogen. So remember the carboxylic acid, it would have been C double bond O, OH.
Okay, sir.
Right, so I'm looking at it after it loses the hydrogen. All right. Right, so that's to sum it up. So the reason why alcohol is the weakest, there's no distribution of electrons, the negative charge, sorry. So the negative charge is solely on the oxygen. So it takes up the hydrogen easily. You don't want that, all right? So that is why it is weak. In the carboxylic acid and the phenol, the negative charge is distributed. However, in the carboxylic acid, it is more distributed. So that is why the acid is the strongest. All right.
So which you said was strongest?
The carboxylic acid is the strongest. Right, so let me put that. So the carboxylic acid on carboxylic acid strongest. Then you have phenol, and then you have the alcohol, which is the weakest. When I talk about most distributed and least, I am talking about the negative charge. All right. Yes, if you on the exam and they ask you about once they ask you about it, these are the explanations you put. It's on yes. So if you get the carboxylic acid, the phenol, and the regular alcohol, you just put back these explanation. Right? And if you're not finished yet, take a screenshot for me. There's something else I have to do regarding the carboxylic acids. All right. Just take a picture for me. All right, I'm going to share the screen now. All right, so the first example, just get a regular alcohol, phenol, and a carboxylic acid. Next thing I'm going to do now, right? All right, by the way, I'm just going to, this word, conjugated, to those, that distribution of electrons between two oxygen atoms, all right? That's due to conjugated effect. Don't know how they will ask you the question, but conjugation, right? That effect, that is what results in the distribution of the electrons in phenol, the carboxylic acid. All right. If you see something about conjugative effect, just know it is dealing with the distribution of the electrons. All right. Just trying to keep it simple here. So if you see that term, just know it is dealing with the distribution of the electrons that we mentioned earlier. All right. The next thing that can happen, right? They can give you 3 carboxylic acids or 2. So this is what I'm going to do, right? Here we have COOH. I'm going to put a chlorine on this. Right? So that's compound A. So there are 2 carboxylic acids, right? The difference is this chlorine atom here. I am going to explain what the effect of the chlorine is. So first, it is a stronger acid. I'm going to tell why. The compound A is stronger acid. All right, so just remember, the acid is, for the acid to be strong, you don't want the negative charge to be centered on the oxygen. So this chlorine atom here is pulling away electrons. It pulls on electrons from the carbon, which in turns, so basically the presence of chlorine causes a net movement of electrons from the oxygen. All right. So once you have an electronegative atom, it is going to pull electrons toward itself. So the oxygen does not have, the charge is not centered around oxygen. All right. So we have electrons being pulled away from oxygen. Compound B, this group, remember when we did benzene, the chlorine is on what? It's an electron withdrawing group. All right. Electron withdrawing group. So all you need to know, once you spot chlorine, just mention that it is pulling electrons away from the oxygen. So it cannot pick up the hydrogen easily. All right. The compound A is a stronger acid. This is because the chlorine atom, let me even keep it shorter. All right. I'm going to make it stay. Just remember that it will pull away electrons from the oxygen atom. All right. For this one, the reverse is happening. Remember, alkyl groups, they are electron releasing groups. Electron releasing. All right. So look, in this, we have the chlorine pulling electron from the oxygen, while this one is releasing electrons towards the oxygen. So in compound B, electron releasing groups are present. So this compound will take up the hydrogen easier than this one for a simple reason. This compound has electron releasing group and this one has electron withdrawing group. Is that clear?
Yes, sir.
Yes,
All
sir.
right. Also, let me just put electron density on the oxygen atom decreases. All right. So that is it. If you are reading, you may see the term inductive effect. All right. Inductive effect. So the pulling of electrons away from an atom or the releasing of it, that is the inductive effect. So the movement of electrons towards atoms or away from the atom, that is inductive effect. All right. So when you see an electronegative atom, that is inductive effect. All right. So the pull on the electrons is the inductive effect. All right. So I don't want to pressure you too much. So just remember that and you'll be good. All right. Take a screenshot for me. And the last thing, so the last 5 minutes, we have to do the bases. All right. So we have to do ammonia. And then we'll end. So this is for the acids, organic acids. We have to do organic bases. All right. So I'm going to clear the screen now. All right, clear. So we're going to use ammonia, methylamine, and then amide. All right, so for the base, right? The one that takes up a proton easily, the stronger the base. All right, so just like with the acid, the more available, the lone pair is, the more available the lone pair is, the stronger the base. The stronger the base. Wait, hold on. I'm going to switch it. I need to put the next one. All right, I'm going to switch this with phenylamine. NH2. All right, so we're going to compare ammonia, phenylamine, and amide. So just remember, before I explain which is weaker, the more available the lone pair is on the nitrogen, the more available the lone pair is on nitrogen, the stronger the base. All right. So I'm going to start with the amide. All right. This is the weakest reason being now, the oxygen atom. So the same inductive effect like with chlorine is the same thing here. So the oxygen atom
Sir, what's that word after the lone is?
So the oxygen atoms pulls on the electrons. So
On the
the
other side.
for the lone pair. Oh, over here, the more available the lone. Oh, let me fix that. Give me a second. All right, so in the amide now, the oxygen is pulling on the electrons, so the lone pair is less available. To take up a proton or to accept a proton. Phenylamine right? So basically, the oxygen atom here, right? So you have oxygen, carbon, nitrogen, and the lone pair. Oxygen is pulling on the electrons from the carbon, and in turn, these electrons are being pulled in this direction. So because the oxygen is pulling on the electrons, these are not as available to pick up a proton. So that is it. So you can put it in your own words, right? All right, I will post something in the community section afterwards. I can see because I'm just trying to keep it simple. So I will post something else and you can spot it. All right. So but basically what happens, this oxygen, it is electronegative. And so you will have the movement of electrons towards it. All right. So once you have the movement of electrons towards the oxygen, this is not as available to take up a proton. All right. And in the phenylamine, if you remember when we did benzene, we said the amine group is an activating group, right? That means the electrons are going inside of the ring. All right. They will be delocalized. All right. So let's go there now. So for phenylamine, is available. Oh, thank you. All right, so for the amines, it's just about the availability of the lone pair, because that is what is taking up the proton. All right, sorry. So in the amide, it is less available than in the phenyl amine. All right, and in ammonia, hold on, let me just put a line here. Ammonia is the strongest because the lone pair of electron is readily available to take up a proton. Let me say to accept a proton. All right, so let me just sum this up verbally. So base is our proton acceptor. This lone pair on nitrogen is what is accepting the proton. If nothing is pulling on it, it is going to easily take up the proton. So ammonia, of these three of them, ammonia is the strongest because the lone pair is available, right? When you get to phenylamine, the ring is basically pulling on the electrons, right? But we just say it is delocalized around the ring, all right? So to keep it simple, in phenylamine, that lone pair of electron is delocalized around the ring. So it is less available to take up the proton. It is the delocalization that is affecting it, all right? That is delocalized, so it is less available. That is why it is weaker than ammonia. The amide now, it is even less available because of the oxygen. So the oxygen pulls the electrons away from the nitrogen, right? So it is less available than in the phenylamine. So when you're explaining, just keep the comparison. Yes, the top one is the amide. So this one over here, right? This is the amide. All right. And if you should get amine, it just means that electrons are what? Being released towards the nitrogen. It is even more available, or the electron density increases. So if you don't get ammonia, if you see carbon, if you see CH3, right? NH2, so if you get an alkyl amine, some carbon and hydrogens, remember they are electron releasing group. So this is better than ammonia. All right, so just make a note. This one here, it is better than ammonia, simply because it has electron releasing group. All right, electron releasing group. All right, so this is better than ammonia. So if you get an amine, if you get an alkyl amine, it is better than ammonia. All right. So what I'm going to erase here, and you just make a note of it because you can get it. All right.
Sir, when you say better than ammonia, you mean like stronger is a
Yes.
stronger acid than
Right.
ammonia?
Yeah. I'm putting it over here. So CH3, NH2, and I'm going to add the reason. All right, so this is methylamine. Let me write the name. It is a stronger base because we know that the methyl group, it is an electron releasing group. So the electron density on nitrogen here, it is higher than this one. Once it is higher, it takes up the proton easier. All right. So for bases, the higher the electron density or the more available the lone pair of electron is, the stronger the base. All right. So it's like the opposite for acids. The stronger the negative charge, the weaker the acid. Whereas in this one, the stronger the negative charge, the stronger the base. All right, just clear the screen for me. I'm really ending now, about 2 minutes. I just have to show you this and then we finish. But under this part, I just have to show you something with amino acid. All right, so just take a picture. I'm going to clear the screen. I'm just going to show you why amino acid can act as an acid and a base. All right, it's now 9:30. All right, so I'm going to clear the screen now. All right, so amino acid. All right, so this is the general structure for an amino acid. Then C double bond O, OH, and NH2. So basically, the amino acid, it has an acidic group. It has an acidic group, and it has a basic group on it. All right. I'm going to show you how it looks in water, acid, and base. So in water, C, H, R, C double bond O, O minus, N, H3 plus. So in water, the basic group will accept a proton. So instead of, all right, let me dry it out. If you want to dry it out, you don't have to dry it out, but let me do it. So it would be NH3, all right, with a positive charge. All right, so positive, right? So if you notice the amino acid, it has a positive charge and a negative charge in water. We call this a Zutter, Z-W-I-T-T-E-R, a Zutter ion. So in water, the amino group picks up a hydrogen and the acid loses a hydrogen. Remember, acids are proton donor, bases are proton acceptor. So you get a Zwitter ion. A Zwitter ion, just a molecule that some group in it will have a negative charge and the next group in it has a positive charge. All right. Now, in basic solution, you will have this happening. In the basic solution, nothing will happen to the NH2 group because it is in a base. But the acid now, if it's an acid, it is going to lose a proton. All right. So this is how it will look in the basic solution. The acid loses a proton. So in a basic solution, the amino acid, it will be negatively charged. negatively charged. All right, in the acid now. This, it is neutral, the positive and the negative cancel, basically. All right, the acid, let me draw the acid now. All right, so C double bond O, in the acid, the NH2 group is going to pick up a proton. All right, and so the nitrogen will get a positive charge. Um, Nothing will happen to this group because it's in an acidic solution. So the overall charge on this is a positive charge. That means in acidic solutions, amino acids have a positive charge. All right, this one is neutral. So in basic, negatively charged. In acidic solution, positively charged. So they can ask you to draw the amino acid of how the amino acid will look in a basic solution. So this is it in a how you should draw it in a basic solution. This is how you draw it in acidic solution. This is how you draw it in water. If they ask you to draw a zeta ion, that is how you draw it. All right, and that is where we end for tonight. Could you explain the formation of water? I still don't get it. All right, so you have to remember when you put, all right, let me just do this. Let's say you have HCl, you have water. The hydrogen will be given up to the water. So you get H3O plus the chloride ion. It's the same thing that happens here. The water, this hydrogen goes to H2O. That is why you get the negative charge here. This is a base, it has a lone pair, it takes a proton from water. All right, is that clear for the person that was asking? So the nitrogen takes a hydrogen from water, and the next water molecule takes a hydrogen from the acid group. That is why it looks like this in water. When it is in a base, then the base takes a hydrogen from the acid group. When it is in the acid, the base takes a hydrogen from the acid. All right. So that's it for tonight. Have a good night. Just look, check out, if you subscribe to the channel, just click the notification bell so when I make any post, you can see it. All right. But Friday is the next, as a certain, maybe Thursday. I will let you know. All right, you are welcome.
Thank you, sir.
All
Have a good
right.
night.
Come on.
All right, sir.
All right. So I'm going to end the live now. But you're all welcome.